Alright, so now that we've taken a look at the chain rule, we've gotten the idea of how the chain rule works, we're now going to look at some very important functions. We've already done the trig function, so now we're going to come back. We've already talked a little bit about e to the x, so we're going to talk about e to the x and the natural log of x, and then move on to exponential and log functions of bases other than the natural base e. So first let's take a look at our graph of e to the x, which we hopefully without a calculator pretty much know that we have an exponential growth curve. It comes across here at our 0, 1, and as exponential growth has a horizontal asymptote here at the axis. All right. So if you think about what would the graph of the derivative be, and what do you notice? I mean, let's pretty much just kind of go through this, that e to the x is one of the most important and most special functions out there. It is pretty much the only function that its rate of change at any x value is the y value that it has, is proportional, and it actually equals its own y value. So if I wanted to know the slope at 1, so at x equal to 1, which would have a point of 1e, its slope at 1 is e. So if I wanted to actually basically give the equation of the tangent line, I don't have to do anything. I say, hey, the point's 1e and the slope is e, and then you could write your equation of the tangent line. It is the only function whose derivative is itself. And that's a very interesting phenomena for this function. Its rate of change is its y value at that point. So if we're taking a look at this and we're going to look at the derivative just to verify that, let's take a look at the e to the x. So let's clear this out and we'll just do our e to the x. And then I'm going to graph the derivative. Let's just do zoom 6 just to kind of remind ourselves. There's our, all right, let's try that again. Zoom 6. So here's our nice exponential growth function, just as we expected. And so now in the second one, I'm going to graph the derivative of n derived, just to prove to you that we have the same function. So n derived, choose number 8, and just reminding you again how to do this. And I'm going to get my vars, my y vars function, and choose y1. And we're evaluating, we want to show it for all the x values, so I choose x right there. And then if you take a look at the graph, you'll see that the red graph that it's drawing, the derivative, happens to lie directly on the graph that was already there, e to the x. And if you take a look at your table and then compare the values, second table, that the values are exactly the same, that its rate of change is the y value at that point. Very interesting function. So now that we've verified it, let's do a proof of this. So again, we're going to go back to the limit definition. So we want to prove that the derivative of e to the x with respect to x is e to the x. All right? So we're going to use the limit definition. So the derivative of e to the x with respect to x, we're going to take the limit as h goes to 0 of f of x plus h minus f of x all over h, which is going to give me the limit as h goes to 0 of e to the x plus h minus e to the x all over h. Now we're going to use some exponent properties here. What I'm basically going to do is I'm going to rewrite this as e to the x times e to the h, because when you multiply and you have like bases, you add exponents, or when you add exponents, you are multiplying like bases. What that does for me is going to allow me to factor out e to the x, e to the h minus 1 all over h. And remember that now, since we're doing the limit as h goes to 0, e to the x is a constant. The limit of a constant times another function is the constant times the limit of the function. Alright, and then the trick to this one, and again we're going to wave our hands just a little bit, kind of like we did in the earlier proof when we were doing the chain rule proof. But what we know is basically the definition of E. So let's just remind ourselves the definition of E. The definition of E is the limit as, I'm going to use H. H goes to 0 of 1 plus H 1 over H. That this was kind of the main definition, limit definition of where E comes from. That if we were to take the limit as H goes to 0 of 1 plus H to the 1 over H, that we would get this number E. Okay, so basically what we know, okay, since you're doing the limit, that if H is small, E is approximately 1 plus H to the 1 over H. If H is small, E is approximately this. And the trick here is that basically, because we're letting the limit as H goes to 0, instead of leaving E in here, what I'm going to do is I'm going to replace E with this 1 plus H to the 1 over H. It's a little bit of kind of pigeon math, but we can do it because in the limits, H is going to be sufficiently small, and these are approximately the same, and so they're going to be heading to the same place. That E, as H goes to 0, this is going to go to E, and since I'm going to 0, I can go ahead and make that substitution. So I have E to the x limit as H goes to 0 of 1 plus H to the 1 over H, and that whole thing is raised to the H, because it's E to the H, minus 1 all over H, which becomes the limit as H goes to 0. These cancel out, and I'm left with 1 plus H to the 1, or 1 plus H minus 1 over H, which is E to the x, limit as H goes to 0 of H over H, which is 1, and the limit of a constant is the constant, so I end up with E to the x, and we're done. And now recognize that you have two versions of this, that you have the version where you have your derivative of E to the x is E to the x, and if you have chain rule, your derivative of E to the u is E to the u times u prime. I also like to write this as E to the u times du dx, because I think that's a little bit more descriptive of what we're doing. We're taking E to the u, and then we're taking the derivative of u with respect to x, and following that in for our chain rule. Alright, so let's take a look at our examples. Let's take a look at example 2. So in this problem, you're basically saying u equals x plus x squared. So du dx is going to be 1 plus 2x. So my derivative dy dx is going to equal, if this is e to the u, okay, if y equals e to the u, dy du is going to be e to the u, and so I need dy du times du dx. So I end up with e to the u times the derivative of u with respect to x, 1 plus 2x. E to the u times the derivative of the u. That's why we kind of use this as e to the u times u prime to kind of get ourselves into our habit of finding our derivative. Another example, I'm not even going to do the u's this time. I'm just going to say what's the derivative. Dy dx would be e to the u times the derivative of u, 4x plus 2, and we'll put parentheses so we know that we're multiplying. All right. Now I'm going to leave these for you to practice on. This one has a, be careful on this, this is e squared, not e to a variable. So this is a constant times x. And then this one, you do have to use chain rule, and you have two chain rules in it. This one, dividing by 4, don't use quotient rule here. Rewrite this as 1/4 of e to the x plus 1/4 of e to the negative x, and make sure you use chain rule on the e to the negative x. All right, and then I'll leave this one for you to try. So do those 3, and we'll check those answers in class next time. Let's look at example 4. In example 4, I'm going to have a product rule, and then I also have a difference here, and I want to find the equation of the tangent line, we'll call that A, and the equation of the normal line to this graph at x equal to 1. So remember that you need a point and you're going to need a slope in order to find your equations. So your point, if I call this f of x, right? So my point is going to be f of 1 to find my y value. F of 1 would be e minus e or 0, because 1 e to the first minus e to the first. So my point is going to be 1, 0. My slope, I need f prime of x, so I'm going to use product rule here and then do the difference. Product rule would be the first function, x, times derivative of the second, which is itself, plus your second function times derivative of the first, minus, then you run through and get to this, derivative of e to the x is e to the x. So f prime, well, let's simplify this while I'm here. This ends up being e to the x minus e to the x. That's going to cancel out, so we get x e to the x. So our f prime of 1 is going to be e. So my slope is e. So the equation of the tangent line is going to be y equals e, my slope, x minus 1 plus 0. And then b, simply, the normal line, the equation of the normal line. I don't really need to do much work. All I have to do is remember that the slopes are opposite reciprocals. So y equals negative 1 over e goes through the same point, plus 0. And then there will be our equations. All right, now in example 5, okay, we have some composition and composition within composition, and we're finding the second derivative. So first I'm going to find dy dx. Right? So the u that I'm looking at first is going to be e to the x squared. But then to find the derivative of that, I need to have another composition, v equals x squared. dv dx is going to be 2x. So then I come here, du dx, okay, would be e to the v. So the derivative of e to the v is e to the v times the derivative of v, which is 2x. And then coming back over to here, this is 2 sine of u. The derivative of a constant times anything is the constant times the derivative. Derivative of sine is cosine of u times du dx, e to the x squared times 2x. And I'll just pretty it up a little bit in case I might need to simplify later. We would have 4x e to the x squared cosine of e to the x squared. All right? So finding derivatives, make sure you work, notice it's 2. Derivative of sine, cosine of u. Derivative of u is e to the x squared, and then the derivative of v, x squared, is 2x. Kind of work your way in. All right? Let's take a look at the next page. Example 6. All right, so here I'm trying to find the derivative, and then here is my function. So I'll do a little work here. I'm going to let u equal 3x plus 4 to the 1/2. So du dx. And this is partly why you have chain within chain within chain. This you should be able to start to do in your head, because you're basically going, it's u to the 1/2. Derivative is 1/2 u to the negative 1/2 times the derivative of u, which is 3. And now I'm going to use that to get my f prime of x. So the derivative of e to the u is e to that value, e to the u, times the derivative of this, which we just found to be that 1/2, 3x plus 4 to the negative 1/2 times 3. Now I'm going to obviously need to simplify because this is written in a much nicer form. So I end up with in the top, a 3e to the square root of 3x plus 4, and then over 2, and then this is a square root of 3x plus 4 goes in the bottom, so we try to figure out which one is our match. So here's the 3/2, but that's got that in the top. Here's 3/2 in the top, so my answer is C. All right, I want to find the derivative here. We've got some product rule and chain rule going on. So I'm going to start running through, because the derivative of a sum is the sum of the derivatives. So I need to do the derivative of cosine of e to the x. So it's a cosine u. Derivative of cosine is negative sine of u times the derivative of u, e to the x, plus, so that just takes care of the first part. Now we come to the second part, and here I'm going to have to use product rule. And remember that in product rule you have two functions, so I'm considering this to be function 1, that to be function 2. So my derivative would be the first, e to the x, times derivative of the second, which involves a chain rule, so I'll come back and do it, plus your second function times derivative of your first function, which is easy. So now I come back and I do the chain rule. So this is sine of u, and sine, derivative of sine is cosine of u times derivative of u, which is e to the x. Now we have to do the work, because we're going to have to simplify this. So I basically have 1, 2, 3 terms. So I'm going to look for things that cancel and some things that I can factor out. Notice that I can factor out everything has an e to the x. So I'm going to pull out an e to the x. This is going to have, actually I don't really need to think about it. If you look at the first and the last, these are positive and negatives of each other. They will cancel out. So really I only have this term here. So I didn't actually need to do the factoring. I pretty much just need to simplify what I have here. And I have e to the x times e to the x. Oh, wait a minute. What do I do with my exponents when I have like bases? E to the x times e to the x times cosine of e to the x. You add your exponents, so it becomes e to the 2x cosine of e to the x. So we're looking for, obviously these are wrong because they have signs. That's wrong, wrong. This one does not have a negative in it, okay, so that's wrong. And then some of my choices that are left, that has a negative in it. This is missing the 2x part, so the answer is B. All right, so let's take a look at example 7. Now here we want to figure out in what intervals is the derivative greater than or equal to 0. So first thing we have to do is we have to find it. So f prime of x, we want to find our derivative. We're going to use a product rule. So I'm thinking of first function, second function. So first times derivative of the second, derivative of e to the 2x would be itself times 2, remember e to the u du, plus your second function times the derivative of the first, 3x squared. Now, because we want to determine when this is greater than or equal to 0, we are going to want to put it in a nicer form, so I am going to factor this time. I have an e to, here's term 1 and term 2. So what do I have in common? They both have e to the 2x, so we'll pull that out. This has an x to a power, this has an x to a power, the smallest power is 2, so we'll pull out an x squared. Okay, taking away the x squared, dividing out the x squared, I'm left with an x and a 2, that gets pulled out. Plus, here, I've pulled out the e to the 2x, I've pulled out the x squared, the only thing I have left is 3. So now I basically want to do a sign chart. I want to figure out where this is greater than or equal to 0. So f prime of x greater than or equal to 0 means we're trying to figure out where e to the 2x times x squared times 2x plus 3 is greater than or equal to 0. Now, when you're doing this, hopefully you'll notice some things. This is an easy problem. E to the 2x is always positive. So it doesn't contribute any critical values to my sign chart. It's always positive. All right, x squared is always positive or 0. It's 0 at 0. So that might be something to contribute to my sign chart. Because when x is 0, f prime of x would equal 0. So that would be a critical number. Okay, and then from here, we know that this is going to be equal to 0. X equals negative 3 halves. So that would be another critical number at negative 3 halves, which would give me a 0. And now, for the rest of it, to fill in these signs, I can ignore these two, because other than those critical values at x equal to 0, which gave me the x-intercept, that this is always positive. So I only have to look at this to determine the sign. So I pick a negative number down here, like negative 10, and obviously that's going to be negative. then it's going to be 0, and then any number above negative 1.5 is going to end up being positive for this value. If you pick, say, negative 1, it would be positive. If you pick 10, it would be positive, and so on. So basically, here's our sign chart. So the answer to our question, f prime of x is greater than or equal to 0 for x on the intervals, positive in between here, and it's greater than or equal to 0. So we're going to do bracket negative 3/2 to 0, and then 0. Actually, do I really need two of them? No, we don't need two of them because 0 is okay. So we want to go negative 3/2 to infinity, and then we're done with that problem. All right, in example 8, find the point where the tangent line to the curve is perpendicular to that line. So the first thing is that you want to figure out what the slope is. So you want it to be perpendicular to this line. So I'm going to first find the slope. I'm going to add y and subtract 8 to x minus 8. So the slope of this line is 2. So the slope of the tangent that we're looking for, so the slope of our tangent line is going to be negative 1/2. So we want to find the point where the tangent line to the curve is perpendicular, so it would have this slope. Now, how else do I find slope? I found it by finding the perpendicular, but I can also find it by doing the derivative. So your slope is also found by doing dy dx. And of course, the derivative of e to the negative x would be e to the negative x times negative 1 e to the u du. And so I'm basically going to set my derivative, my slope equals dy dx, and I'm going to set that equal to negative 1/2. So my negative e to the negative x equals negative 1/2, and then we have a little review of solving. E to the negative x would equal 1/2, and then we need log, so natural log of e to the negative x equals natural log of 1/2, which these are inverses, so they cancel out. Negative x equals natural log of 1/2, or x equals negative natural log of 1/2. Now, and then just as a side comment, depending on how your multiple choice might play out, you do realize that this is the same as using your log properties, 1/2 to the negative 1, which is natural log of 2, just in case you see that in your multiple choice. But this is an acceptable answer for the problem. And so, did I answer it? Find the point. Okay, so we now know that the x value of the point is negative natural log of 1/2 or natural log of 2. And then so the y value of the point we find by plugging that in. And so we would end up with e to the negative natural log of 2. Well, actually, I think I like the other version better. Let's go back to the one with the negative, because then I can cancel it out. So I would write my point as negative natural log of 1/2, and then e to the negative natural log of 1/2 ends up being e to the natural log of 1/2 or 1/2. So my final answer in its nicest form would be natural log of 2 and 1/2 for the point. And that's just also make sure you read the question you actually answered what they ask you for. Alright, so we're going to stop this video here, and we'll pick up the next one on the derivative of the natural log.